Hello, this is Mrs. Cribb. I'm going to talk you through the periodic trends. You're going to need to pull out your notes for periodic trends for Chapter 5. And we talked about in class, we may have talked about in class, depending on how far we got, that the atomic radius of an atom decreases as you go from left to right. So it gets smaller as you go from left to right. And it increases as you go down. And how is the atomic radius determined? They take two atoms that are the same kind, and they find the nucleus of each atom, and then they measure the distance between the two nuclei, and they cut that distance in half, and that is the radius. They don't actually measure the distance from the nucleus out to the edge of the electron cloud, because it's a cloud and it's hard to figure out exactly where the edge is. So it's still about the same thing though. So the radius of the atom actually gets smaller as we go left to right. And we can see that here. We have potassium with 19 protons and electrons, and gallium with 31 protons and electrons. And gallium is actually smaller in radius than potassium. And why is that so? It's smaller because potassium, which has 19 protons and electrons, and gallium, which has 31 protons and electrons. When you compare the two, the positive charge for potassium is a 19. The positive charge for gallium is 31. The negative charge for gallium is 31, and the negative charge for potassium is 19. And you can kind of think of that as rubber bands, like potassium has 19 rubber bands pulling the protons and electrons close together, but gallium has 31 rubber bands pulling them closer together, so it's pulled tighter. So the more protons and electrons they have, the tighter it pulls, the stronger the charge, the electrostatic charge is between the protons and the electrons. Just like stronger magnets pull in quicker, weaker magnets don't pull in so quickly. Think about it like that, but also think about it, the number of rubber bands or ropes pulling those guys together. As we get more protons and electrons, more rubber bands pulling them tightly in. Okay, so with that said, you can tell that vanadium with 23 protons and electrons would be larger than selenium with 34 protons and electrons. And the other thing about atomic radius is that it gets bigger as you go down. And the reason it gets bigger as you go down is you're adding more and more energy levels. So let's look at the periodic chart again. Lithium has 2 energy levels. Rubidium has 5. So as you add energy levels in, it quickly gets larger. Lithium has 2 energy levels and rubidium has 5. So if I add 1 energy level, 2 energy levels, that's lithium. Rubidium, 1 energy level, 2, 3, 4, and 5. That was a terrible circle, but you can see 1, 2, 3, 4, and 5. Rubidium has 5 energy levels. Its atom is much larger. So if it adds another energy level, it's automatically larger. So let's compare a couple of these guys. Get a bigger eraser here. Erase all this. And let's determine, well, which ones would be larger. Okay, if I compared barium 56 with 6 energy levels and chromium 24 with 4 energy levels. So barium 56 with 6 energy levels and chromium 24 with 4 energy levels. So barium and chromium. What do we know? Barium has 6 energy levels. 1, 2, 3, 4, 5, and 6. Chromium has 4 energy levels. 1, 2, 3, 4. Well, automatically you can see barium is bigger. Now, barium has 56 protons and 56 electrons, and chromium has 24 protons and 24 electrons. So even though chromium has smaller charge, and you would think it could be a bigger atom because they're weaker and it doesn't pull in, and barium has more charge, and you'd think it'd be smaller atom because more of those rubber bands pulling it in. Since it automatically has more energy levels, it's automatically a larger element. Okay. Erase all this, and we'll get going with the newer stuff. In general, I gotta turn my own notes over. There we go. In general, the radii of atoms decrease left to right as the atomic number increases in a period. The outer shell electrons are held progressively more tightly. Odd wording. And the average distance from the nucleus to the outer energy level shells decreases. Atomic radius increases when moving down a group or column in a periodic table because the principal energy level is added. So every time we go down, we add one more level, the atomic radius automatically gets bigger. Okay? Ionic radii. When we make an ion, remember you make ions by adding or taking away, removing. You make ions. Cations are positive ions. Remember that? Positive T in the middle there. They are smaller than the parent ions because they have fewer electrons and then the fixed positive nuclear charge. This means that the nucleus is stronger and pulls the electrons in tighter. Many times the outer principal energy level is lost. The outer principal energy level. Anions are negative and they result from the gain of electrons and are larger than their neutral atoms. An excess of negative charge is more effective in shielding outer valence electrons from the positive nuclear charge. Also, added negative charge tends to repel. Remember, electrons are all negative. Like charges repel, and so they push away from each other, and that makes the electron cloud get bigger too. So it tends to repel the negative electrons in the outer shell or in the valence shell, either one. Okay? And it would be in the same shell we're talking about, in the same shell. All right, let's draw some pictures. We're going to draw, now in your notes, this portion over here was incorrect, so you need to change it so it reflects this. Okay, the parent ion for chlorine has 17 protons, and if you look over here, chlorine 17 protons, 3 energy levels. I'm just going to draw the valence electrons, okay? There's 17 protons, there's 2 in the first energy level, there are 8 in the second energy level, and there are 7, 1, 2, 3, 4, 5, 6, 7 in the third energy level. 7 valence electrons. So chlorine has energy level 1 with 2 electrons, energy level 2 with 8 electrons, and energy level 3 with 7 valence electrons. It has one little hole there because it really wants 8 electrons. So 3 energy levels. We have 17 protons. We have 17 electrons. Add that together, we have a 0 net charge. This is chlorine, and it's neutral. Okay? Now, chlorine really wants this extra electron because of something very important called the octet rule. Sorry for this horrible handwriting. It's really hard to do this, just so you know. All right, and the octet rule says that 8 is the magic number for the atoms. They all want eight valence electrons. And so they do what they can to get 8 valence electrons. They either try to get more to get down to level 8, to get up to level 8, or give some away. Chlorine has 7 valence electrons right now. See these 7? 2, 4, 6, and 7. If you can find one more electron to fill that spot, it will be super happy. And that's what happens to the anion, because now it's going to be a negative ion. All right, we're going to have 17 protons still in the nucleus. We're going to have 2 electrons in energy level 1. We're going to have 8 electrons in energy level 2. And then we're going to have our 7 valence electrons that it normally has, but it's going to find this extra electron, and it's going to come in and fill that spot. And energy level 3 has now got a complete octet. And it's an anion, and it makes it happy with that octet. It has now 17 protons, but it has 18 electrons. And when you add 17 positives and 18 negatives, you get a -1. So chlorine is a negative ion here. It's an anion. And this anion is larger than the neutral atom because of these things up here. Particularly, the electrons are repelling each other. So they're pushing away, making it bigger. And the electrons that push away have to be in the same shell. Okay, now what about sodium? Sodium is element number 3 with 11 protons and electrons. So 11 protons, 11 electrons. There's 2 in energy level 1s, and there's 8 in energy level 2s. That's, in energy level 2, the 2s and the 2p, and 2 plus 6 rather. 2 plus 8 is 10, and there's 1 more valence electron out here. Sodium has 1 valence electron. See that? 1 valence electron. It's in column 1. 1 valence electron. Had the 1s2, the 2s2, and the 2p6. That's the 8, and then 1 more. So 8 plus those 2 is 10, plus the 1 from right here makes 11. Okay? So sodium, parent, has 11 protons. I don't know where my pen went. 11 protons. And there it is. 11 electrons. Okay, my pen's starting to give me trouble. All right, so it's neutral, has no charge. I haven't used the mouse now, so forgive me. All right, so what happens with the cation? Let's see if I can get this pen to work again. Good. There we go. Well, with the cation, we have the 11 protons. We have the 2 electrons in the 1s. We have the 8 electrons in the 2s and the 2p. So, 2s has got 2 and the 2p has 6, and added together that's 8 valence electrons. And then we have that 1 valence electron in the 3s. Well, that electron goes away. This electron, in fact, it usually is given to something like chlorine. That electron goes away. When that happens, what happens is this energy level right here. When that entire energy level disappears. So we could erase this entire energy level. And as that energy level goes away, and that electron goes away, we can see that sodium, the cation of sodium now, has oh, goodness gracious. The cation of sodium now has 11 protons and only 10 electrons. Those are negatives and those are the positives. Add that together, we get a +1 charge. So now what we have is sodium with a +1 charge. It is a cation. All right, so now let's move on to the brand new stuff. The first ionization energy. Okay? All right, that's what this goes here. The first ionization energy is the minimum energy required to remove the first electron from its outermost shell to make a cation, because if you remove an electron, you're making a cation. This increases from left to right. Okay? Remember, the radius is smaller, so the electrons are closer to the protons in the nucleus. And this makes them harder to pull away because the charge, the attraction between the positive and the negative is bigger because they're closer together. And I think of the nucleus as the mama. So mama nucleus and her babies are the electrons. And the closer the babies are to the nucleus, the harder it is to take them. You won't take her babies if they're close. Okay? The first ionization energy decreases from top to bottom. So higher energy levels are farther away, making the electrons easier to pull away. Mama nucleus is getting farther from her babies until she is so far away she can't get to them, and an electron napper comes along, should be Anne, and easily takes one of them. Okay? So the farther the electrons are from the positive nucleus, the easier it is to take them. So as the radius gets bigger, the first ionization energy gets smaller. It takes less energy to steal the babies. Okay. Now, electron affinity. If you have an affinity something, you really like it. I have an affinity for pumpkin spice lattes and an affinity for chocolate. All right, the amount of energy required to add an electron to a neutral atom to form a negative ion is electron affinity. So we're talking about an atom here. We're talking about unbonded atoms. And that's important. Here we're just adding an electron to an atom to make an anion. It's the opposite of ionization energy. Ionization energy is the energy to take away an electron. Affinity is the energy to add an electron. So let's look at Mama Francium over here. Mama Francium way down here, 87. Notice that means she has 7 energy levels. So Mama Francium is a very big mama with lots and lots of energy levels, and she has 87 baby electrons. And so that last baby electron, her valence electron, is an energy level 7. Okay, very far from the nucleus. It is super easy to take her babies. She has 11 electron babies. She will gladly let you adopt one from her because watching 87 babies is impossibly hard. But please do not give her another one to keep up with. So affinity, if your electron affinity is low, your first ionization energy is also very low. They're the same. If affinity is low, the ionization energy is low. Okay, this measures how strongly atoms attract the additional electrons. For incomplete sublevels, like SPD and F, most elements will easily accommodate the additional electrons. They'll easily take them. They want to complete that octet, magic number 8. Okay? Now, electronegativity is super important. And this is something we're going to deal with a lot. Negativity. It's the measure of the attraction between the nucleus and the valence electrons. Most cases, it's determined for atoms bonded. So that's something that's different from affinity. Electronegativity deals with bonded atoms. Affinity deals with unbonded atoms. Okay? So in most cases determined for atoms bonded in molecules which share electrons. So we're talking about covalent molecules. Really a measure of an atom's ability to attract and hold electrons, and it's determined mathematically. So just determined with math, the electronegativity. Fluorine is the most electronegative element on the chart. It has 7 valence electrons. It really wants to complete its octet. It only has 2 energy levels. See, there's energy level 2 or period 2. Fluorine is in period 2. So it's a small atom. So here we have fluorine. Okay, it's a small atom. It has 2 energy levels. The first energy level is the 1s2. The second energy level is where you find its valence electrons. It has 7 valence electrons. One little hole there. So it's small. So it's holding tightly those electrons. It needs only one more to complete the octet. So it will quickly go hunt down somebody's electron and fill that empty spot. So it has a high affinity for electrons, and its electronegativity is also going to be high because when it bonds, it forms things quickly where it can take away an electron. All right, I want you to go into your textbook and read this example problem. Make sure you understand it. We'll probably go over it some in class as well, but I want you to understand it now. Think about how big the electrons are, the atoms are, and also there's a mnemonic device that you can do for figuring out electronegativity. Notice fluorine is way over here. The closer the atoms are to fluorine, the more electronegative they are. The farther away, the less electronegative they are. So this area over here, low electronegativity. This area right here, high electronegativity. If you look on a chart for electronegativities, which I will probably give you, fluorine's electronegativity is equal to 4.0, and that's the highest it can be. The highest electronegativity it can be. So the closer to fluorine, the greater than the electronegativity is. That's not the way to do it. The greater the electronegativity it is. Okay. Fluorine has a high electronegativity, so really that doesn't work either way. Hopefully you just understand what I'm trying to say. The closer to fluorine, the greater the electronegativity value is. Let's get a pen. Okay, so remember a couple of things. Big atoms have, it's easier to take their electrons. Okay, and they want to complete an octet. So do you either, that's always important. So if you need to add more electrons to complete the octet, that's what they'll do. That means high electronegativity. If they need to get rid of it, they'll have a low electronegativity. And we saw earlier that sodium, way up here, sodium really wanted to get rid of it, so it had a very low electronegativity. And if you look on the chart, sodium is way over here, far away from fluorine, a very low electronegativity. All right, now here's some additional problems. Which has a larger atomic radius, titanium or gallium? Titanium or gallium? All right, here's gallium, and here, where's titanium? Titanium, right here. So titanium has 22 protons. Gallium has 31. They're in the same period. So which one would be larger? Titanium. Which is larger, magnesium or phosphorus? Magnesium is an energy level 3, and so is phosphorus. So which is larger? Magnesium has fewer protons, so it's larger because the more protons, the more rubber bands pulling it in tightly. So magnesium is larger. Which is larger, magnesium or barium? Magnesium has 3 energy levels, barium has 6. Well, if it has more energy levels, it's automatically bigger. So barium is larger. Which is larger, xenon or argon? Xenon and argon. Xenon has more energy levels. It has 5 energy levels. Argon has 3 energy levels. So xenon is automatically larger. Okay, which then has a larger electronegativity? lithium, or oxygen? Okay, we're going to look and see how close they are to the fluorine. There's fluorine. Okay, so oxygen is right next to fluorine, and lithium's way on the other side. So oxygen has a greater electronegativity. Chlorine or magnesium. Chlorine is right next to fluorine. Magnesium's way on the other side. Chlorine has a greater electronegativity. Sodium or francium. Sodium is right here, and francium is right here. Francium is much bigger, so it's easy to take away its electrons. Sodium is much smaller, so it's not as easy. So sodium would have the bigger electronegativity. And then barium or beryllium. There's beryllium and there's barium. Barium is much bigger. It's easier to take away its electrons. Beryllium is much smaller, harder to take away its electrons. So beryllium would have the higher electronegativity. And which has the larger ionization energy? Okay, let's look up here. Titanium or gallium. If you have a big atomic radius, it's easy to take away its electrons. So the ionization energy for gallium would be bigger because gallium is smaller. The babies are closer to the mama. Magnesium or phosphorus. Magnesium is larger. The babies are farther away from the mama, easy to take it, so the larger the ionization energy goes to the smaller atom because the babies are closer to the mama. Magnesium or barium. Barium is larger. That means that the babies are far away from the mama, so it's easy to take it, harder to take magnesiums, so magnesium has the higher ionization energy. And xenon or argon. Xenon is larger, so argon has the higher ionization energy. Okay? And that's where we're going to stop.